Welcome to the 50th anniversary of the discovery of plate tectonics by Dan McKenzie and Jason Morgan. My co-chair and tech expert today is young Jason Morgan. I'm Richard Hay. I thought by now there would already have been Nobel Prizes for plate tectonics, probably for Jason, Dan, and Fred Vine. It's possible scientific revolutions are too big for Nobel Prizes. Einstein never got one for relativity. But Nobel Prizes are a dime a dozen compared with scientific revolutions, and I can't even conceive of how satisfying it must have been to have created one of the great scientific revolutions of the 20th century. Rather than me summarizing Hank Frankel's book to start the session, I thought you'd rather hear Jason Morgan's thoughts, 50 years after the 1967 AGU meeting where he first presented the quantitative theory of plate tectonics. Jason Morgan, then at Princeton, now at Harvard, continuing a tradition he began 50 years ago of not having an abstract describing what he'll talk about.
So it was December 65, I wrote and published a paper that's titled Here, working with Hess and Elsasser, and I was trying to have convection in the mantle. This was a uniform fluid. It was a perfect sphere sinking or perfect cylinder sinking because you did everything with analytic functions and very simple geometries then. And what I'd worked on was a sphere sinking, and it pulls down the surface. And so the gravity effect that you get is, well, this you're real close to the missing mass up here, and it pulls it way down, but this goes the other way, but it's 1 over r squared, it's much further away. But you have a pull down and you have a gravity low. And to try to test this, I used data from Lamont. This was a very elaborate study by a lot of people from Lamont. And they used data from 30 submarine dives and about 30 two-ship refraction lines. And this is the Puerto Rico Trench, north and south. And this is, if you see the little tiny red dots, they're the data. And the line that they got by varying the MOHO fluctuating, they could then calculate gravity. They thought they knew all of the upper layers from the seismic refraction. And when I looked at this, I went at the point of view that an isostatic island is high gravity over the island because there's a lot of rock near you. There's a big root, so out to the sides there's a negative. And to make this, I just took the profile and flipped it and made an isostatic symmetrical island, subtracted it from the data, and I had something that I could fit. And this was the paper I had, and there was interesting comments on the paper from Lamont. And at the following year, the talk I planned to give at the AGU was on the extension of not just a uniform fluid, but sort of a high viscosity lithosphere and a low viscosity asthenosphere underneath it, and trying to model that. And so the abstract I submitted was on this other subject. And you notice the end of the session and everything ran low, and there were a lot of people that wanted to have lunch, I guess is the. But in the first week of January, this paper by Bill Menard came out, and in his book, which was one of the 2 places that I learned my education on the nature of the seafloor, the marine geology of the Pacific, he had stated and made a point that the great fracture zones in the Pacific were all great circles. And in this paper, he said, no, I was wrong, because he plotted the great fracture zones on a mnemonic projection, where a great circle is a straight line. Mnemonic is also called the great circle projection. And yes, some are, but when I looked at this, I noticed that the ones up to the north curved up a little bit, and the ones to the south curved down. And it looked exactly like a figure that I'd had in my navigation textbook. That this is the mnemonic projection. You put a point at the center. Any plane that goes through the center makes a great circle, but where it intersects a map plane, it makes a straight line. But notice, the small circles aren't straight lines. And I saw that connection and sort of immediately set about, are these all concentric about the same pole? And this was, didn't have Xerox then, but you had sort of a wet copy that's a little blurry. And some of these lines are calculated on top, but if I had a pole that was in Siberia, it would pretty much fit all of the great things. Now, it had no meaning, except back when the Pacific was spreading, it could be opening up that way. And so this is just a cleaner version using a figure from his book and not from the science paper. And this pole really seems to mostly fit those great circles. But the test was in the Atlantic, and I went and found maps of the Atlantic fracture zones. This pole at about 65 north is very different from the Bullard Everett Smith pole, but you can pretty much fit them. And the medal was, if you are opening things on a sphere about a pole, you get the fracture zones would be concentric circles, and also further away you'd have faster spreading. And this was looking at individual magnetic anomaly rates that Fred Vine and I did from sort of published profiles, mostly. Towards the end, other people were getting rates for this. And it fits this pattern. So that was it. I made a copy of the talk that I brought. I think it was some kind of a blue ink that you could make about 20 copies before they got real blurry. I don't know. It's pre-Xerox. There was a Xerox on campus, but it was in another department in another building. And those figures that I just showed were all reproduced by this. When Xavier found his copy, he printed it. Now, I'd like to point out, this is 64, and George Bacchus published a Nature paper. It has everything that I said in 67. He has the formula for the opening, being sort of like a sine function, the further south. And George gave me this paper when I was at Scripps in 69 in the halls. And he says, you probably haven't seen this. And he said, nobody did. He said that he wrote a proposal to have funding to have someone digitize Project Magnetic Flights so that he could do spectral analysis. And he thought as you got down further from the opening, there'd be longer wavelengths. The funding wasn't proposed, didn't get funded, and he dropped the idea because he was then working with Freeman Gilbert on the inverse theory. So that's my story, and thank you.
Jason, thanks. We'll move on to the formal presentations, but could you just describe what you felt like when you first had the idea?
No.
Okay.
You know, it was a good idea. I mean, I knew that.
Okay, the next talk will be by Don Forsyth, and it's not chronological in the sense that Don's big contribution to plate tectonics sort of came at the end of an early phase of really rapid discovery. And it's a paper by him and Sayueda on the driving forces for the plates in a really interesting way of looking at it. AGU is going to take him away to be rehearsing now for the next couple hours, as he's the Ewing medalist this meeting. So he's going to be talking on, I'll set you up in a second. He's going to be talking on both his thoughts then and what he's thinking about more now, which is much more what I know him for, and also the Ewing medal is probably recognizing him for in his work on the evolution of the oceanic upper mantle, mid-ocean ridges, understanding the strength of continents, and a large number of other things. So here you go.
Okay, so as Jason just said, I came along after the revolution, really, and I regarded McKenzie's and Jason Sr.'s and Lynn Sykes' work as being the absolute truth. It was already known, and I just started from that point of view. I had no idea there was a big revolt that preceded it. So if you Google plate tectonics driving forces and try to find some useful figures, this is what you get. The point of this is that the plate tectonics move around because of convection in the mantle. But other than that, this figure is totally misleading.
Okay.
So you find dozens of variations on this theme where basically they show large-scale convection in the mantle with upwelling beneath mid-ocean ridges, downwelling near the subduction zones, and you have to dig really far to find something else. But this is just totally wrong. There's no deep upwelling roots beneath ridges of hot upwelling material extending deep into the mantle. Basically what's happening is the plates are moving apart, and that passively drags material away from the ridges, and you get passive upwelling beneath the ridges, which then undergoes some partial melting just due to pressure release of upwelling hot material. We also know it's passive. We knew this very early on because as ridges approach trenches, nothing happens. You get the same crust you got when it was in the middle of the ocean as you do if the ridge is about to subduct beneath the continent. And to be a large-scale convection of that kind, you would have to have upwelling immediately next to downwelling. That just doesn't happen. So we know that upwelling beneath the ridges is mostly a passive response to plate separation. And seismically, we can tell that this is obviously more recent, but we've known this for a long time as well, that there are no deep roots beneath ridges that you can see seismically. You see anomalies, function age of the seafloor, getting faster as you go into the seafloor, maybe extends down to 150 kilometers, maybe as much as 200, but by the time you get 250 kilometers, there's no correlation of velocity with age of the seafloor or nothing associated with ridges. We do see high velocities associated with trenches. So we can see the subducting plate with this global tomography, but we can't see the upwelling. And so the shear velocity is a function of age of the seafloor in the Pacific and the Atlantic, but best data comes from the Pacific. It's a function of age, and it can basically be described by cooling of a plate conductively to the surface. And again, it's basically just a passive motion overall. Oops. But if you dig deep enough, you can find, I should point out first, that there's this pronounced low velocity zone, which we believe is low viscosity as well, and part of it at least could contain partial melt. If you dig deep enough, you can find other illustrations on Googling that look more like this, which show an asthenosphere which is much shallower, no concentrated upwelling from great depth, pressure release melting beneath the ridges, producing some melt that comes out to form the crust. Show a strong slab pull, which we expect from thermal models, that this is by far the largest density contrast in the mantle below the immediate ridge. So we expect a strong slab pull from the cooling of the plate sinking down into the mantle. So that in this figure is correct. This says buoyant magma pushes up, driving plates apart. That is not really what happens. The melt mostly is removed to make the crust. There's very little melt within the mantle itself at any one time. And you do get some ridge push from either, you can look at it as an elevated ridge makes greater pressure, which tends to push the plates apart a bit. Or you could think of it as an uplifted mantle that the plates sort of slide off the uplifted asthenosphere. So you can find these visions. Most of the one that's being transmitted to the public is completely wrong. So working with SEA Ueda, beginning as a class project in 1972, I believe it was, we tried to look at the forces in a simple way of looking at what pushes or pulls or resists the motions of the plates. You need to know, besides the forces that are making the plates move, what resists them. If you don't look at that, you don't understand the system. So we put in drag force at the base of the oceanic plate, a drag force at the base of continents, which could be different. Could get a suction towards the ridge if the plate's rolling back. You have a pull of the downgoing slab. You have resistance to plate sinking, viscous resistance to the plate sinking, friction along transform faults. And we looked at that system, parameterized the form that we thought the forces might have, and then required that there be no imbalance of torques. The plates are moving at a constant rate, and the forces have to balance. So basically what we came up with is that slab pull is the dominant driving force. Resistance to penetration into the lower mantle is probably the strongest resisting force. And you get some push from the ridges, but it's probably an order of magnitude smaller than the pull from the trenches. And in order for this to work, you have to have very little drag on the base of oceanic plates or low viscosity. So I haven't done anything on this in the last 40 years or whatever it is. In a lot of ways, this picture still holds, but people are now doing highly sophisticated 3D dimensional modeling that automatically balances the forces and the momentum and everything else. Often produces the same results, but this result is actually non-unique. It depends on how you parameterize the forces, what you end up getting as a result. But my interest has been more focusing on this ridge part and looking at how much of it is active and how much is passive. So we had the melt experiment back in 95, 96, which was the first large-scale deployment of ocean bottom seismometers on the seafloor. They were out for about 6 months, 5 months, I guess. And we had about 50 instruments, about half of which worked. And we recorded teleseismic body waves and surface waves propagating across it. It may look kind of strange that we have this at an angle to the ridge. That's because this points to a large amount of seismicity in the Southwest Pacific. We wanted to line it up so it would get basically along great circle lines. So this is a paper or an issue of Science that summarized a lot of the results. The melt area has a very straight ridge with no offsets, but there's anomalies in the sense that there's a lot of seamounts on the west side and relatively few on the east side. You can see the background subsidence is faster on the east than on the west. And when you look at Mantle-Bouguer anomalies, they're asymmetric as well. And what we found from the surface wave and body wave models is that the lowest velocities in this area within the array were actually west of the ridge axis, and sort of rapid increase in velocities to the east. So this is sort of a artist's conception idea that there's an asymmetry in mantle structure with much more rapid increase in velocities on the east than on the west. Anomalies may extend down to about 150 kilometers or so. And our initial explanation was that there may be flow coming in from the west, from the superswell region of hotspots in the central Pacific toward the ridge. And you get rapid increase on the east of the ridge. If you have flow this way and you encounter a thickening plate, the flow is going to be driven downward. And if there's melt present and you remove melt during the upwelling process, when you start moving the material downwards, it's going to instantly freeze because you've changed the composition. So that was our explanation for why it was asymmetric. Katz has suggested that it's asymmetric partly because of the hotter materials in the west, but that triggers small-scale convection locally, and a little bit of magma being retained in the matrix provide a little bit of buoyancy, and you have upwelling, and then you could have downwelling to balance the upwelling and bring material down that way rather than pushing material across the ridge from one side to the other. So we have another experiment that is relevant to that, and that's the Cascadia initiative. Doug Toomey is the primary leader of the deployment phase of this. And these are all ocean bottom seismometers deployed in two sets, one in the north in the first year, back in the south in the second year, and then back north again and back south again. So altogether there's 4-year deployment of ocean bottom seismometers on about the same spacing as you have in the EarthScope US array. And so it's 4 years later, we have much better data than we did in the melt experiment. I just want to point out that there's seamount asymmetry here as well. A lot of seamounts on the west side again, very few on the east side. There's the Cobb-Eichelberg seamount chain, and axial seamount is right on the ridge here. And there's a few seamount chains up to the north. So a big improvement came from conceptual advance of Crawford and Webb. Ocean bottom seismometers at long periods are very noisy. And it comes from two sources. One is ocean bottom currents that turbulently interact with the ocean bottom seismometers. And that's mostly horizontal noise, but if there's any tilt at all, that horizontal noise gets translated onto the vertical component. And the other is sorts of noise is long wavelength ocean gravity waves that penetrate to the seafloor and create pressure variations that make the seafloor move up and down. So it turns out you can use the horizontal components to predict what the turbulent noise interaction is and remove that. So you go from here to this. And then if you correct using the pressure records for the vertical motion, for the pressure effect of these long period waves, you can correct it down to this. So we went from this noise level, which limited the period range we could use before, to something that looks like this, which is absolutely gorgeous, at least from a seismologist's point of view, and greatly increased the period range that we could use and the signal to noise ratio. So this is the basic result. This is our starting model. We built in a starting model to invert the surface wave data, which basically just shows increase in velocity with age. This is a depth of 25 kilometers. And what we see is when we add the data in to this starting model, we get something that looks like this. There's a low velocity anomaly associated with axial seamount, but all along the Juan de Fuca Ridge, the velocities are lowest just to the west of the ridge axis, and then there's a very rapid increase in velocities on the east side, much more rapid than you expect from conductive cooling alone, and the velocities get to be faster here than what you expect from conductive cooling at this depth. So our explanation for that is small-scale convection. This is two profiles, one running through here, another one 100 kilometers north. This is the model input model, so basically nothing expected to happen or much of the plate down below about 40 or 50 kilometers. And then this is what we find. North of the axial seamount, we find this rapid increase in velocities and increase down to about 70 kilometers, 60 or 70 kilometers. And across axial seamount, we see this rapid increase also, but then another higher velocity region below the plate over here. So our explanation for that is small-scale convection induced. Overall, it's a passive system, but melt retention will lead to an active component of upwelling, especially if you have a hot spot here where the velocities extend deeper. The upwell and then the downwelling that's associated with the upwelling to balance things immediately eliminates melt. So you get a rapid change from having melt present to no melt present as you come to a downwelling region. And that can explain this rapid change. We don't have data onto the west of the ridge, so we don't really know what happens over here. And this is just another depiction, paper by Burns et al. It just came out very recently, arguing the same basic interpretation, but arguing for some carbonate related melt extending down to about 200 kilometers. So basically, upwelling beneath mid-ocean ridges is largely passive, driven by the separation of the plates. The resulting elevation of the ridge provides a modest driving force that helps push plates apart. And then pressure release melting of upwelling mantle and consequent melt retention buoyancy locally creates a dynamic component of upwelling. So overall it's passive, but locally at shallow levels there's a dynamic component, and that causes rapid increases in seismic velocity beneath the seafloor and the asymmetry that we observe. Thanks.
Any questions? Okay.
One of the key ideas in the plate tectonic revolution was Tuzo-Wilson's transform fault hypothesis, partially based on Lynn Sykes' 1963 paper while he was still a Lamont grad student, that showed oceanic seismic activity was almost exclusively confined to the parts of fracture zones between offset ridges. Lynn was inspired by the Pittman and Hertzler L10 and 19 profile to test Tuzo's prediction of the wrong sense of motion on transform faults, I believe at the time expecting to prove Tuzo wrong, but instead providing compelling proof of seafloor spreading in his classic 1967 paper on faulting on mid-ocean ridges. He then collaborated with Brian Isaacs and Jack Oliver on another enormously influential paper, their 1968 New Global Tectonics paper, corroborating the seismic predictions of plate tectonics. There were many great papers coming out of Lamont in those days, and those were some of the most influential. Lynn Sykes of Columbia University in Lamont, today talking about his road to transform fault in 1963 and long-term precursors to recent great earthquakes.
Okay, thank you. So I'd like to give you some background of where I started in the 1960s, or in fact in the late 1950s when I was an undergraduate. And I was told at that time at MIT as an undergraduate, as many people learned in North America, that respectable young earth scientists should not work on vague and false concepts like continental drift. And the reason being that continents cannot plow through strong oceanic crust. As a result, I did not take continental drift seriously until the spring of 1966, but I was very glad that I did then. I think we have a somewhat similar situation today with earthquake prediction on various timescales, which long-term prediction of about a decade or so interests me a lot. And various people have said that it's impossible and that earthquake prediction is for fools and charlatans. So with that background, I'd like to go back to 1962, 63. This shows an area very inaccessible of the southeast Pacific Ocean, just to the north of Antarctica. The mid-ocean ridge system is shown here in the light color. I got involved in this area certainly and the plate tectonics aspects and transform fault aspects purely by serendipity. I started my PhD work, as many people at Lamont did, on short period seismic surface waves, and my study was of ones that cross oceanic areas. So I had waves in a large area of the southern oceans, including this area. And I had to use sources that were earthquakes. So on this, at about 55 south, you can see that the earthquakes are oriented with my relocations just about east-west. I might say before I did this, the earthquakes in this area were scattered a lot in their locations. So I found that I needed to relocate them to get better distances and origin times for these events. And that was solely to get better estimates of the speed of certain seismic surface waves. But I found when I did that and relocated these earthquakes using a program that Bruce Bolt had written shortly before that, that I was able to see that the earthquakes follow the mid-ocean ridges. How can I point?
There's a tiny mouse here. How about this? Just use this. Just use this.
Okay.
That's a pretty big mouse.
Okay, so the earthquakes follow the mid-ocean ridge system. They take a direct turn 1,000 kilometers to the east and then resume their northeasterly trend along the East Pacific rise. In my paper that I wrote on this, I concluded correctly that this was another fracture zone that was not known, what we now call a transform fault. Also in my abstract that I wrote on these earthquakes and their distribution was that the earthquakes did not continue across the mid-ocean. They did not continue along the fracture zone beyond the two ridge crests. But at that time, I didn't make anything of that. Tuzo Wilson used some of my data from this and other fracture zones that I looked at for his idea of transform faulting. My idea at this time was that if there were 1,000-kilometer long features like this that were unknown in the world, that was important to work on. And I did that for the next couple of years in some other places. I also then went on to work on relocating earthquakes that were then called island arcs, now subduction zones, in the Western Pacific, and I was able to define the seismic zone extending from the surface down to as deep as 700 kilometers in several places. I had almost finished that work when I went to Fiji to work with Brian Isaacs on deep earthquakes. While I was there, James Dorman wrote to me about a paper that Tuzo Wilson had given and then published in Nature, but I didn't do anything on it until I got back to Lamont in November 1965. I quickly finished that work on the distribution of earthquakes and island arcs, and so in the springtime of 1966, I thought a lot about testing Tuzo Wilson's hypothesis. Okay, so one of the sets of data that I had was from a new network of similar instruments that were well calibrated, called the Worldwide Seismic Network, and also a Canadian network of similar stations. So I didn't know much about earthquake mechanisms, but I decided that this was important to do. And the thing then that I thought about it that was a good thing to do, and then in the spring of '66, I was shown the magic magnetic anomaly profile of Pittman and Hertzler across the East Pacific Rise, just to the north of that fracture zone that I studied. So the next morning, I started working on earthquake mechanisms. And within a month or two, I was able to derive a few of them. And I very quickly found, after I did two of them, that Tuzo Wilson was correct. And as you can see here from the study that I published in 1967 of some of the earthquakes along mid-ocean ridges and along the fracture zones is number 2 and number 3, that they are both strike-slip motion on nearly vertical faults, with the motion being indicated by these arrows on the two sides. So they fit Tuzo Wilson's idea of transform faulting, and they were opposite from that of simple offset of the ridge crests, which was a common hypothesis before that. So this was my introduction to transform faulting and ultimately to plate tectonics. And now I'd like to switch to a very different topic that I've been working on more recently of long-term earthquake prediction. One of the features that we've had for the last 15 years is some really good seismic data and geodetic data, GPS data, at several places that have had giant earthquakes or great earthquakes. This is one in northern Chile, the Quique earthquake, a little bit larger than magnitude 8. It occurred in a place that had previously had an even larger giant earthquake in 1877, and then had not ruptured since then. So this place was isolated in not having interfering seismic activity, much like the place that Pittman and Hertzler studied for their magnetic anomalies in the across the East Pacific Rise. So one of the features we can see here is that I have summed up what is called the seismic moment as a function of time. Since the time these data were first produced in 1976. And we can see that instead of being just a gradual increase or a linear increase, that there is a substantial acceleration of seismic activity in the 5 or 7 years before this great earthquake. Also, other work that others have done for this region is on what is called B values. B values are a measure of the number of large to small earthquakes. And with the black above, this is outside the region that broke in this earthquake, and we can see there's no significant change with time, whereas within the rupture zone that there is a decrease in the B values. And B values have been found in the laboratory in which close to failure that with increasing stress, B values decrease as indicated here. And then finally, I'd like to say a little bit of work about where we might go with long-term prediction. One is that all of these earthquakes that I looked at, about 8 of them, giant earthquakes, occurred in what are called seismic gaps, places that had not had great earthquakes for a long time. We also found out from GPS data that these were places that were largely locked in the period of stress accumulation. Another phenomenon that's been found in the last 15 years is slow seismic slip. So I have put a great emphasis on looking for this, as others have, as being a new phenomena that we didn't know about prior to about 20 years ago. And a significant thing was before the giant 2011 Japanese earthquake. There was about a 1 to 2 decade increase in slow slip on the downgoing plate boundary, as inferred from measurements at the surface using GPS. And I've mentioned accelerating seismic moment and decreased B values. Another phenomena is looking at small earthquakes at nearly the same place. And for example, in Japan and a few other places, there has been an increased rate at the same place in repeating small earthquakes. And of course, foreshocks have long been difficult to identify as such ahead of time, but if some of these other phenomena are going on, we can certainly take a look and see if there's an increase in activity of this type. So this is something that interests me now, and I would argue that long-term prediction is a subject that's worth working on. So thank you.
Are there any questions for Lynn? I have one. Can you explain what it felt like when you saw the L10 and 19 profile?
Yes, as soon as I saw it, I knew that they had something really big, that the magnetic anomalies were symmetrical for plus or minus 500 kilometers across the East Pacific Rise. And by that time, I had done enough work on locations of earthquakes and leading up to the work that I did the next day when I saw this paper on earthquake mechanisms, that they had done something really important.
Thanks. Are there any other questions? Yes, one over here.
Do you recall, I believe, the original skepticism to Cascadia subduction zone being active?
I'm sorry, the subduction zones being what?
Cascadia, the letters
Right. I think this is an indication that you have to be willing to learn and to admit that you've been wrong, which I was there. So I think that with long-term earthquake prediction, we have to pursue that subject, but be willing to learn and make mistakes.
Thank you. Any other questions? Okay. Dan McKenzie had just received his PhD. Dan McKenzie had just received his PhD from Cambridge and was working at Scripps when he realized that the Bullard, Everett, and Smith continental reconstructions depended on Euler's theorem and independently discovered plate tectonics. In his classic 1967 paper with Bob Parker, The North Pacific, an example of tectonics on a sphere, he showed that slip vectors could be used to determine plate motions and rotation poles, and that the North Pacific was behaving as a rigid plate. That was the first published plate tectonics paper in Nature 50 years ago this month. He followed that with another of the most important plate tectonic papers ever written, the last of the truly revolutionary kinematic ones, the 1969 McKenzie and Morgan Evolution of Triple Junctions paper. Dan also did seminal work on the development of sedimentary basins, and his papers have been enormously influential in an amazingly wide range of fields, including geophysics, structural geology, geochemistry, and planetology. 25 years ago, I called him one of the most impressive earth scientists ever. That now seems inadequate. Dan McKenzie of Cambridge University is talking on the thermal structure of oceanic lithosphere.
Thank you. I want to go back and start with Harry Hess, because what Harry did, which is shown in this paper, and Don Forsyth has said a little bit about this, and almost all of this picture we now believe to be wrong. The central issue, which really held everybody up for a long time, was the notion that there had to be rising sheets beneath ridge axes. And if you have that, how in the world do you have symmetric spreading of the ridges all around Africa? It just made no sense at all. And I had a long, Tuzo Wilson was at that stage working in Cambridge, and I was a graduate student, and I had a long talk with him about it, and neither of us could understand what was going on and how this could possibly be. And the real thing about plate tectonics, I think, is that it is a kinematic theory. It doesn't worry about what's happening underneath. And once we realized that, both Jason and I essentially got there really very quickly. Jason has priority. Curiously enough, I was actually in the session where he talked about it, but his abstract, as he said, was about something quite different, and I was an earnest young man. I read abstracts and went to different talks. So I left knowing that actually the Lamont people were going to be extremely upset with his reinterpreting their data, right? And this was not at all something you did in those days. So I left because I didn't actually want to see that, blood on the floor. And then Jason talked about something quite different, but that made very little impression at the meeting, except to Xavier, who went back to Lamont and set about doing things. So essentially, the idea of Harry's, which was critical, was that actually everything happened along a line. And that really released the whole of our understanding. And from that, we went then very quickly, where are we? I'm not doing this right. This is a picture from the paper I published in Nature, which I must say it's the first time it ever happened. Bob and I sent it off airmail to Nature. We never got any reviews, we got no proofs, and it was published on the 30th of December, 1967. Right, it just made it. Right. Something which I've been grateful for John Maddox ever since. But it's not a good paper as far as the presentation of data is concerned. I had yet to learn the importance of actually producing good pictures showing the data, and I've always been embarrassed by that. Here is actually the data plotted in the same oblique Mercator projection, which we used actually at that time to produce the picture. And I think this is an enormously much better picture than the one we published, but that's simply because I've learned how to present data since then. The other thing I did then, which was not actually a result of, this was also in 1966, was to worry about this problem of what happened beneath ridges. And I came back, I was hugely impressed. I went to a meeting in New York at which Lynn talked about what he just described here, and Fred Vine showed a whole series of magnetic anomalies. And it was quite clear, I think, to everybody in the audience that this was the end of the speculation. And it was obvious then that, okay, you just simply went ahead with the kinematics. That had to be right. So I went back to Cambridge and decided that actually ridges, if we were going to talk about the whole thing, then ridges also had to be kinematic. It had to be just simply plate separation, as Don Forsyth talked about, which produce what we see. And the picture, which is still in Google, is the one at the top. This is actually taken from a paper by Ron Oxborough in 1980. He should have known better by that time. The bottom one is what I think most of us now believe. And so I did the sums on this. I did it analytically. And I was trying to do two things at the same time. I was trying to both produce an elastic layer, right, which could support the topography, what we now call TE, the elastic thickness, and also produce the heat flow. And this is a plot taken actually from Sayre Ueda's, one of Sayre Ueda's papers, right, showing the heat flow. And you can see that the scatter is enormous. Right? So at that time, this top picture was actually little more than a sketch. It was an idea as to how to think about these things. But as you can see with the fit of the data, right, it's just appalling, right? It's not a good fit. And we had really, at that stage, no clear idea as to why the fit was so bad. That came later with the discovery of the black smokers. But the bottom picture is from a paper by Parsons and Sclater 10 years later, where they took essentially exactly the same model and the same mathematics and showed how extraordinarily accurately it reproduced the depth age in the oceans. And this, on me, had a really profound effect because it showed that these ways of looking at things through physical models were the right way to think about things. We were quite used to, I was trained as a geophysicist, so I was quite used to using physical things to make measurements on the Earth, but the notion that that was how we should actually think about it was something quite new. And that really came, for me, from this piece of work which Barry Parsons and John Sclater did. And I'll show you in a minute that they were actually too careful. Right? There's a gap here. They would only look at the depth, right, where they had magnetic anomalies, because then they knew their ages. And this gap here is the Upper Cretaceous quiet zone, where they didn't trust the dates. So there was a hull. There's one point here, which is just a little bit above the line, and as you'll see in a minute, that's important. I'm not used to this thing yet. So this is now our modern view of all this, and it looks the same, but it isn't. Because unlike Barry and John, we now have measurements of the thermal expansion coefficient as a function of temperature, right? Also the thermal conductivity as a function of temperature. So none of these things now are adjustable. But the picture looks just the same, not quite. You can see that the spacing between the isotherms here, right, at the top, low temperature, is quite different from the bottom, and that's because the thermal conductivity changes by about a factor of 2, and this is important from the point of view of getting the isotherms right. And that matters from the depth of the earthquakes. You can see the earthquakes here are all in a region whose temperature is below 600 degrees centigrade. You can also see something which Alistair Crosby found, right, which is when he redid this, read the depth age using what were then much more trustworthy dates from the quiet zone, you can see that actually it gets shallower and then goes down again. And this, I still believe, is a signal of the fact that the boundary layer has gone thermally unstable and the bits are dropping off the bottom. Cold regions are going down. Here is a picture of this is from Hasterek's work, of the collecting the heat flow observations, getting rid of all that noise, and you can see it really fits beautifully. To get it to fit here near the ridge, you have to take into account the fact that the upwelling is actually producing all the melt, and that cools it down. There's also a suggestion out here, right, that something like this is happening in the heat flow. So that's really what we learnt from looking at those things. And I keep on doing the wrong thing. And Greg Hausman and I and Barry Parsons looked at the instability which could produce the warming and actually cause the lower boundary condition to be constant temperature. And that's shown here with a model which just says that as the boundary layer thickens, it goes thermally unstable. More recently, right, here's some work by Mark Hoggard in Cambridge, has actually collected all these things up, and here's his plot of depth versus age. This is quite scatter. This is looking at from Crosby. You can see, right, that this is slightly different. Right, there's a slight offset of about 100 meters. Whether that's really tightly constrained, that I'm not by any means sure about. But the basic picture looks the same. The new thing is coming from seismic tomography. Here on the top is the age of the Pacific, and this is the velocity at a depth of 150 kilometers. And this does not look like a plate model. We did not expect to see high velocities, right, a change in the velocity here associated with the ages as you go from the eastern to the western Pacific. So I recently have had quite a close look at this, and the first thing I did was, keep on doing that, was to parameterize the velocity as a function of temperature. And in order that the argument wasn't circular, I used for this parameterization a half-space cooling model rather than a plate model. And that is essentially important from the point of view of making the argument logical, but doesn't actually make any difference to the parameterization because that's really controlled by what happens beneath the ridge where it's very hot. And you can see what you get is what is very clear now in many studies, and it was clear right back to Ian Jackson, right, first study of this, is that the relationship between the velocity and temperature is extremely nonlinear as you go to high temperatures. And the slope is shallow here and then becomes very steep. And this is important because it means this part, right, the velocity is up here, high temperatures, the velocity very much is very strongly controlled by the temperature and gets it, that you can use that. These are just simply the fits, right, to nodules, to the velocity at 50 kilometers, and to the velocity at 70 kilometers, which are the result of the parameterization. So what you can then do is actually stack all the velocities according to age, and have a look at the variation of the temperature with depth beneath the oceans as a function of age. And here are the ages. They were binned in 10 million year bins, and you can see that the fit is quite remarkably good, right, until you get to 65 million. And then stuff from the surface wave velocities is slightly hotter. And then by the time you get to 135 million, it's back to fit the plate model. And I must say I'm quite astonished by how good this fit is, and by the fact that actually this is behaving in just the same way as we saw with the depth age. So what we can do is integrate that temperature structure and look at how it behaves. And the black line here is just simply this is just simply the plate model, fixed temperature at the bottom. Right? This one is from the analytic expression, the red curve here is from Barry Parsons and John Sclater's curve. Here's Crosby's one with the bulge. Here's what comes, and this is from Hoggard's depth age, the running mean, and this is what comes from the surface wave tomography. Now, my suspicion is that this is going to improve and that this behavior of the surface wave tomography is real, but perhaps more important is how extremely good the fit is of the surface wave parameterization and tomography is to the plate model. Right? And this, I think, is the final straw in understanding the temperature structure of the shallow part of the mantle. The other thing which I was curious about was this variation with the age. And this is now taken, this is an oblique Mercator projection on the so-called absolute pole of motion of the Pacific. And these, I've cut it, right, in sectors of width of 10 degrees about that pole, and I've stacked then the velocities in here and determined the temperatures. Because my view was that if actually it was correlated with the plate motions, it wasn't correlated with the plate age, so maybe it was correlated with the plate motions, and that the stuff is falling off right from the bottom of the plate, making this high velocity region in the Western Pacific. And I could see that if I thought if I actually stacked it by sector on the absolute pole. Here is the interior temperature, right, from calculated. This is the 13-15 degrees potential temperature, and this is then in terms of that stacking of degrees about the absolute pole. And what you can see is that there really is not anything there. There's really no signal, right, at the deeper depth, which suggests to me that that variation of velocity with position in the Pacific is the result of overall convective circulation rather than anything related directly to the plate motions. So, yeah, keep on doing the wrong thing. So let me just come to conclusions. I don't think that plate tectonics is alive and well and boring after 50 years, and I don't expect its central features now to change. The thermal structure of the oceanic and continental lithosphere, the thermal boundary layer of the convection, I think also is now actually quite tightly constrained by surface wave tomography. Mantle convection is responsible for gravity and residual depth anomalies, much melted generation, and we can look at all that now in various different ways. But there's no agreement yet about how much transfer is going on across 670 kilometer depth. And this is, I think, going to be a major question which arises in the next few years. I think, again, seismic tomography is going to help greatly on that. Deeper down, I think we're in real trouble because of resolution. So, when I come to the end of my career in the earth sciences, I think our understanding of geodynamics is incomparably better than it was in 1963 when I started as a graduate student. And I'm delighted to have had the chance of taking part in this advance. Thank you.
Any questions for Dan? I have one. Same as the question for Jason. How did it feel to you when you first had the idea?
I knew. The question is which idea, really? The work I did on the temperature structure of plates, I did while waiting for my examiners to read my PhD thesis in Cambridge. And I was very happy with that. I was not sure it was right, but it certainly resolved the question. How it felt like to have the basic idea of plate tectonics, which that you could describe everything by rigid motions about Euler poles. I thought that was really, as Americans would say, neat, right? And I mean, it took Bob and I only a few days to work out all its consequences, because actually if you're thinking in the right way, it's as obvious then as it is now. I think my major concern about all that was that for quite some number of years after that, I didn't have a proper job, right? And this stuff was now being taught in high schools. Was I actually going to be redundant before I even got a proper job, right? That was some concern to me, right? But I was very happy to have been involved in that, even if I never had another decent idea.
Are there other questions for Dan? I think I see one here.
Yeah, Dan, I'm intrigued by your thermal anomaly in the Cretaceous log normal rod. You mentioned it might be a denomination. Did that drive cupola wonder?
Woof, heavens. I doubt it. That instability, if it's a thermal instability, is not exactly delamination. It's much more that the boundary layer goes unstable and produces blobs. Because the boundary layer is quite thin, that's falling off, the horizontal scale of that has to be really quite short. And this is, I think, our problem in seeing it in the gravity and things like that. My guess is that its spacing between the sinking regions in that region is no more than a few hundred kilometers. And I can't quite, I mean, I've never thought about what you just said, but I would rather doubt that I could make true polar wander from that.
If anyone has other questions, could you wave your arms or yell out? It's very difficult to see from up here. Okay, thanks. One of the most important marine geophysicists in the early days of plate tectonics was John Sclater, a Cambridge graduate who was a postdoc at Scripps and roomed with Dan McKenzie while Dan was discovering plate tectonics. The 1971 McKenzie and Sclater Indian Ocean paper was a masterpiece, a manual of how to use plate tectonics to work out the tectonic evolution of ocean basins that guided a lot of our work. But John is probably best known for the Sclater curves. In the early days of the revolution, the heat flow pattern was actually used to argue against seafloor spreading. John combined heat flow with other marine geophysical data to produce his iconic plots of heat flow versus age and depth versus age in classic papers with Jean Francheteau and Barry Parsons. His work showed that the heat flow was consistent with plate tectonics and that a plate model could explain remarkably well both the seafloor subsidence and the heat flow pattern decreasing with age. And his Sclater, Anderson, and Bell paper used deviations from these curves to discover ridge jumps. John Sclater of Scripps, today talking about the title on the screen.
Okay, let me get up here close enough. Well, Dan's a really hard act to follow. And he has been for most of my career, but also he and Bob have been tremendous helps in the things that I've done. As my talk is going to be somewhat different than the ones that have come before, I need to have a confession. I actually started wanting to be a historian and get a scholarship to go to Oxford. But I had a fairly bright father who did research in medicine. And he looked at me and he took me straight in the eyes and he said, "John, first of all, you can't spell. Second, you write English badly. And third, if you're a historian, you have to sit in a library and you're too hyperactive to do that. And fourth, it does not pay well." So at that point, I changed essentially to chemistry, but I've been doing a little bit of chemistry. I've never done any chemistry since then, and since I did it actually in high school. So with that confession, we start into what is the talk that I'm going to give here. Of course, I suppose most of you are worrying, what is the connection between Wegener, okay, and Sierra Prieto? Well, the first thing, can I just get this, do I have to do it down here or up there? Yeah. Where is it? How does it get onto here? Okay. It'll be there? Yeah, I'll just follow it through here. So, okay, let me just go for a couple of papers. Okay, the first thing I wanted to do is to get into the early history. I had a graduate student, Peter Molnar, at MIT, who pointed out to me that those of us who are geophysicists never looked at the literature, and in fact we never read Wegener, and Wegener had done almost all of the thermal work that we needed to do for constructing these thermal models. Well, for this talk, I made the mistake of actually going back and reading Wegener, where Steve Hellinger says, yes, it might be. And actually, that's true, that in fact, Wegener had in fact done a really major, really good job in terms of looking at the elevation anomalies on the ocean floor. He actually argued that they were created thermally by the intrusion of hot material, and that he only had a thickness actually of 10 kilometers where he wanted to produce the uplift, but the uplift he got was 300 meters. It's very easy to see that, in fact, if he'd had 100 kilometers, it would have been 3,000 meters, which is exactly the difference between the depth at the ridge axis and the depth that you get in the deep ocean basins. The next person that I had an influence from was Arthur Holmes. Arthur Holmes in 1944 wrote his classic, well, it was actually done in 1929, but published in his textbook in 1944, where he showed, in fact, that there was convection in the upper mantle. He put the whole basaltic layer together with the continents, had everything being pulled apart from the creation of eclogite in the trenches, but he had a real problem with the mid-ocean ridges. With the mid-ocean ridge, with the intrusion process, and he really couldn't find out one. And if you look at some of his other diagrams, they're kind of crazy in terms of how he actually gets the basalt in there that he sees on the ocean floor. Now, I believe the reason why both of these people didn't actually take this thing any further is because they didn't read an oceanography book, okay? The person who's a classic person in oceanography, in fact, he coined the name, is John Murray. And John Murray not only was best actually known for the Challenger expedition and writing up, I think it was 35 volumes. And I think basically nobody believed that he could do really good science as well as being an administrator and doing that, or making money and doing that on top of things. But he wrote a great book in 1912 with Hort in terms on the depth of the oceans. And the first, let me go through this thing. Okay, and what he did is he produced a really interesting map, and I just missed the thing on it. Have I got it off here? Oh yeah, there we are. Where you saw that you had a central mid-ocean ridge down here that actually mapped very well the continents, or mirrored the continents on either side. Now remember, this is 13 years before the publication of Wegener's paper, and something like, 33 before Hess. The other two things that he did that were really major is that he, from his background, he'd partially been at medical school before like Darwin, he went to Edinburgh and then left. He also argued from the dissolution of carbonates, which he knew it out and was the first person to point that out, on that in fact they dissolved it by a depth of about 4,000 meters, or maybe actually 3,500 meters. He actually went and took cores in the oceans, and he found that the red clays that you have in a deeper ocean than that lay on top of carbonate material. And he argued quite persuasively from this that in fact you could only get red clays on top of the carbonate if, in fact, you'd had substantial subsidence. You could also only get them there, if you look at by inference, because the red clays were 3,000 kilometers from the ridge axis, that you'd had a huge amount of horizontal motion. And now I'm actually going back to my thing that I really like, of course, to begin with, which was history. I simply don't know how. Well, certainly Arthur Holmes could not have actually read this book, this famous book by the father of oceanography. I certainly can understand that Wegener didn't, because I got a suspicion that at the time that actually Murray did this, maybe the data were classified and they didn't want the Germans to have it, so the German maps that were actually produced at this time that Wegener used were actually very much short of information and almost totally useless. So I'm going to spend a little bit of time with thermal models, but not very fast. Here's actually the first thermal model of the ocean floor, and the first thing that actually got it going was a paper by Xavier Le Pichon. In fact, it was in Lamont. He was actually trying to please Maurice Ewing and show that plates didn't actually move around. And in terms of what he got, the thing was this: he got the subsidence too small from the plate model he constructed, and the heat flow was too low. But in fact, as we know now, of course, he forgot the effect of water, and he didn't know about hydrothermal circulation, which affected the heat flow. Okay, then this is the model. Actually, what Dan did is Dan actually produced a theoretical solution for this problem. It's actually the basis of all theoretical models from that, and this is just to show a reference to what the work that he did. Now, the interesting thing is that Norm Sleep was the first person to actually apply this, and he showed in the Atlantic that there was a very good relationship between depth and age. I worked with a number of people on this. Let me just go on. I don't need to look at that slide. I'm a person of time. And we actually came up with myself, Roger Anderson, and Lee Bell. What we have here is the depth age curve, which in fact is which Dick Hay referred to. So they have this relationship that the heavy black line is the data, and they have a dashed line there, which was the theoretical model. When I actually went to match with the observations, okay, I didn't use the actual theoretical model. Bob Parker said, "Cripes, what you need to do is use it this time, and the only people are going to believe is the actual observation. So you plot it when you're trying to match everything around. You actually use the observational data rather than the theoretical." And again, that's because he could see that the actual fit, that the observational data was so powerful. Then with Barry Parsons and I, we found out that in fact, well, you found out from Clive Lister's work that in fact the hydrothermal circulation was damping out the heat flow. I'd done some work with Dan on the on the Galapagos spreading center, where I'd seen in well sedimented areas that the heat flow really matched what you would expect from the theoretical curves. And then what I did at the same time as this is that what we did is that we looked at this thing of the square root of age. That was what the theoretical would say in terms of the heat flow out to 80 million years. We then looked at the depths, and the interesting thing from the depth, I'm having trouble getting this thing back on again. Oh, here we are. Okay, you can see that there's a difference here. In fact, what you're seeing is a shallowing of the depth. The heat flow, because the effect only takes place much at double the temperature, double the time as it is for the depth. And in fact, the thing that we have here is what's called the boundary layer model, which is essentially using a half-space model. And basically what Barry and I were out to do was to show that the data wasn't fit by the boundary layer model. Now, the other thing that we saw, which was interesting, is that we could actually see that little difference. And what we wanted to try and do, and Barry and Dan got into this right after we actually saw that there was that difference, and used this, again, I'm having trouble, okay. And they used this to look at the plate model. They actually got the flattening simply by doing convection in the upper mantle under here, small scale convection. These are the thermal plumes, which was added by Tony Watts and John Hillier here in terms of the uplift that you get. And they can put these two things together to give a very good match for almost all of the depth data on the ocean floor. The same thing that we had here is that below it, going to turn that back. Oh boy. We went below it. Let me see if I can actually find, let's go back one. Okay, this is boy, I'm hitting the thing, it's very, very active. So, okay, here's a curve of what we would expect in terms of the real temperature with depth in the oceans. Okay, and then here's the effect of the boundary layer, and I'll just go on from that. And that actually works out really well in terms of the thermal boundary layer and the mechanical boundary layer on the surface and their explanation of the depth anomaly. So, okay, now the first application I was going to go into, I don't really have enough time. It was looking at the continent, oh boy. It was going to look at the difference between what was happening on the heat flow through the continents and heat flow through the oceans. In terms of this, one back. Okay, what you have on the left-hand side here is the depth is actually the heat flow versus age on across a profile, and well, any generic profile. You can see it's higher. You go down on the right-hand side, that's over the continent, it drops, and you can see a change of the ocean-continent boundary. Here's the work that was done by Lucaso in 2008. In fact, what he was able to show is exactly that's what you see in the northern part of the Gulf of Aden. And, oh boy, that was me. The effect that you can see is actually a real drop. The reason why I bring this in is because what is the last thing that I'm going to talk to, and is probably as interesting as, for me, as what I've done in the past. Okay, we wrote a proposal to CONACYT and the Mexican Energy Department to try and get work, to try and do the heat flow work in the Gulf of California, and to look at this particular problem that I showed you before. But just as we got to start in this profile, in this program, we discovered that Prohl had actually found some very high heat flow values. Okay, I need to get it right. Uh-oh, why is this thing? Oh, we're moving away from this. Yeah, okay. Let me go back. Now what's happening now? Just click. Oh, okay. And now can I go back? Yeah. Yep. Okay, and then, okay, up here is the heat flow profile that we had. Prohl finds some high values there. We were very critical of these high values because you had too short a probe to get it deep enough to get out of the effect that you have from having a one-year cyclical period in terms of the temperatures. But we decided to drop all the stuff that I was doing before. And because the Mexican Energy Department was actually supporting us, we thought if we actually had an important thing here, if we dropped it, we'd never get any money again. So we actually started then to do let me put this thing. So boy, I'm having trouble. Let me talk about the line across the Gulf of Mexico. At this point, you can see up on the top left, that's the line of heat flow stations that we took. And then we took the profile and we actually looked at it, and you can see the profile itself as you go across. You can start on the left-hand side. This is in the Wagner Basin, or the northern basin of the Northern Gulf. Then into the center of the basin it drops. But the spectacular thing was where Prohl had actually done her data. As you go over on the right-hand side, over the top of the Wagner fault, the Wagner fault, what you end up by doing is you get very high values that are in the order of 1 watt. Okay, and in some places when we did a cross profile to the north of this, this was given to us by Fabian Newman, who was actually the person who was taking all the measurements and wrote this stuff up. We actually get values that go up to about 2 or 3 watts, and you can actually contour them. Okay, what you have here is what was done in terms of the contour. Okay. On the central side that you have there is the actual temperature. It's the heat flow anomaly. It's about above 2 watts. It's about 10 by 10 kilometers large. You can actually calculate from that what the overall thermal gradient is. The conductive thermal anomaly is going to be, and that ends up about 200 megawatts. Now, to the north of this, on the extension of the Cerro Prieto fault, there is the Cerro Prieto single-source power station. It's the largest single-source power station in the world. Okay, if you look at these numbers that you're seeing here, they're kind of incredible. If you look at the conductive anomaly over Cerro Prieto, it's somewhere between about 4, okay, and maybe 10 to 15 megawatts. The anomaly that we're seeing in this particular area is about 280. And so the difference between Cerro Prieto in terms of the thermal anomaly around it is about 10 to 1, is about 10 to 50, at least 10 to 15 to 1. I mean, it's huge. The problem here, of course, in terms of geothermal power is the difficulty that you have is of using this, because what the power comes out of is the advective component. Not, in fact, the conductive component is the actual advection of water. So in summary, what I wanted to say is that, first of all, in terms of looking at the historical perspective, I presume that Wagner and Holmes must not have never read Murray. Though problems that were there in terms of the early attempts to get thermal models right, In fact, by the end, as Dan showed, we have a really spectacular match to the plate model and most of the observations of depth in the ocean floor. And finally, part of the work that we've done is to actually discover a huge geothermal anomaly in the northern part of the Gulf of California that's clearly on a continuation of the Sierra Presa Fault. Okay, thank you.
Questions for John? Well, I certainly have one. You were rooming with Dan McKenzie when he discovered plate tectonics. What was that like?
I don't know if I'm right, if I can say a non-Bowdlerized version. I liked it tremendously, but I had real competition for time with my girlfriend, who was at that point wanting me to engage with her. And in fact, when he did the 1967 paper, it was really interesting because I left to go to sea, and he was I can't remember what he was working on, but by the time I came back, he'd actually worked it out, and actually had the whole of that system completely worked out. And then he worked with Bob Parker, and it was wonderful to work with Dan because the thing was that you had the chance to actually work on this stuff before anybody else got to it, and so a lot of the things that he did had really clear observational implications for them. And what we ended up by doing is being able to get into the depth age thing very fast and also into the heat flow age very quickly. And the other thing, of course, there was very, very good students at Scripps at that time.
Other questions for John? Okay, thank you. The biggest change in understanding plate motions has been the change from the early models using marine geophysical data and million-year magnetic reversal timescales to using more instantaneous data such as GPS. The leaders in this effort have been the group including Richard Gordon and his ex-students Chuck Dumetz and Don Argus. Their models have included Newvell and Morvell on million-year timescales and Geodvell based on space geodetic data. Their latest Morvell model includes 56 plates. These increasingly better approximations of plate motions may be pushing plate tectonics to the limit of what the theory can explain, and rigid plate tectonics has been so successful that areas where it appears to break down are of great interest. Richard Gordon of Rice will present today's Argus, Dumetz, and Gordon talk. Richard Gordon.
Well, thank you. It's a privilege for my co-authors and I to be able to present in this session. And I have to say the talk that Peter just gave for Tanya is a really tough act to follow. So I can't possibly be nearly as entertaining, but I'll try to see if we can't find some life in what Dan has described as now boring plate tectonics. So I'm going to range over a variety of subjects. I'm afraid I'm not going to get into very much depth on any of them. It's just the nature of this kind of talk. And sort of my summary here, let's see, pointer, is this the best way to? Yeah. Okay. All right, well, so classical plate tectonics, if that's not an oxymoron, I'm not sure, has narrow plate boundaries, but we now recognize many wide or diffuse plate boundaries. And so this is one of the major ways I think plate tectonics has evolved since its original conception. So it was recognized early in the continents, and I'm sure Peter Molnar will be talking about the broad deforming zones using it in the continents. We're probably using a different terminology, but we think of these as diffuse plate boundaries, and one of the things we've contributed to is establishing that these occur in the oceans as well, and roughly the same fraction of lithosphere is part of a diffuse plate boundary in the oceans as in the continents, but the strain rates are lower. Covers about 10 or 15% of Earth's surface. I'm going to propose the idea, I've proposed before, it hasn't caught on, of the idea that in the oceans it's useful to think of component plates and composite plates. And I'm also going to point out, and not get into much depth about it, but the poles of rotations within these diffuse oceanic plate boundaries between different oceanic plates tend to lie in the middle of the boundaries. And this is very different from what we see for the narrow plate boundaries, where the poles of rotation are far away in just mathematical descriptions of what's going on. This suggests maybe we can put some physical interpretation to what these poles are telling us. Plate rigidity, the central tenet of plate tectonics, is an excellent approximation, but it's not perfect. And we believe there's small, significant non-rigidity. John Sclater talked about, and Dan McKenzie talked about thermal contraction. Doesn't occur just vertically, also occurs horizontally, and on the plate scale can add up to a few millimeters a year. And as Dan McKenzie and Don Turcow pointed out long ago, the Earth's not a sphere. As the plates change latitude, they have to deform to accommodate this. Space geodesy can help us address this plate rigidity question. And the biggest thing that we see from space geodesy in terms of non-rigidity, or short-term non-rigidity associated with the response to the deglaciation, most recently since the last glacial maximum. A challenge to plate rigidity that I'm going to put in front of you in this talk is that when we look at plate circuit closures, if we assume the plates are rigid, when we add up the motion of 3 plates around a triple junction, should sum to 0. But in the Pacific, we see that for Pacific Nazca Cocos plate around the Galapagos triple junction, it sums to 15 millimeters a year, which is huge. We don't understand it. It's probably not a challenge to plate tectonics, but it's a huge anomaly we just don't understand. Okay, then finally, turning more to space geodesy, what can we do with it that we couldn't do with marine geophysics? It expands the scope of the plates that we can look at. We can include plates that don't sit next to a mid-ocean ridge, which we had to just kind of ignore what their motion was or guess it before. So that allows us in the West, in North America, for example, to treat the Sierra, Nevada, and the Great Valleys of microplate, analyze deformation in the basin range, and then also go the other direction, look at motion relative to the Pacific plate, and partition out the deformation across the San Andreas fault system. And also explore the steadiness of plate motion. I mean, the youngest magnetic reversal was 780,000 years ago. We don't have any finer time resolution on relative plate motions, but with space geodesy, we can look at motion over a decade or decades. And it looks like it really is very steady, which most of us were expecting for a variety of reasons, but we do see some significant differences, both speeds ups and slowdowns. All right, let's go into the details of this. Okay, maybe I can move this up here. Okay, so here's a world plate boundary map, really a sketch map, something I did together with Seth Stein over 20 years ago, and we show all the diffuse plate boundaries as stippled areas. So here's the big India-Eurasia deforming zone that we're familiar with, the Cordillera in North and South America along the west coast, but also in the oceans. And the most spectacular one is here in the Indian Ocean. We have a deforming zone here, another one here, a smaller one over here. And also we see one here in the South Atlantic and then here between North America and South America. I'm going to talk just for a minute about what we see here in the Indian Ocean, more specifics of the plate geometry. And this is where the composite and component plates come into thinking. We long thought of there being a single Indo-Australian plate, which we assumed was a rigid plate, and its boundaries are defined by traditional narrow plate boundaries, mid-ocean ridges, transforms, subduction zones. But we now think of this as actually being 4 distinct plates in measurable relative motion. We have an India plate up here, a Capricorn plate right here. The biggest one is the Australia plate, and then we also have a small Macquarie plate down here. These shaded in regions are the diffuse plate boundaries. So and across these boundaries, we see hundreds of faults in a single profile. There's so many blocks in there that you need tens of thousands of plates to talk about plate tectonics. It doesn't make any sense. It's much more logical to think of it in terms of continuum in which you define its properties by many fewer adjustable parameters. Another interesting thing that we see is that the poles of rotation between these lie in the diffuse plate boundary. So here's India, here's Capricorn. This little dot is where we think the pole of relative motion is. So they're converging on this side, they're diverging on this side with the pole of rotation in the middle. So we get thrust faulting over here, normal faulting over here. Here's Capricorn plate, here's Australia. We think the pole of rotation is about here. Again, they're converging up here, they're diverging down here. And so this looks like this converging zone, which is also accommodating convergence between India and Australia, is all kind of merged together. You know, we've only just kind of sketched out where it is here, but the area of this is huge. It's a gigantic fold and thrust belt, folds of the entire lithosphere, 200 kilometer wavelengths, thrust mechanisms that have hypocenters down to 40 kilometers. So it's a profound fold and thrust belt, very unlike the ones we see on the continents. And the area of this is the same as the 48 states, or as I tell people in Texas, where we think of Texas as being the biggest thing anyone could possibly imagine, you could fit 12 Texases into this. All right, and then also down here, we think the polar rotation between Macquarie and Australia is right here. So this is something phenomenologically very different from what we see happening with the narrow plate boundaries. So when we go, so these would be the component plates: India, Capricorn, Australia, Macquarie. We think they're all tightly bound mechanically, even though in relative motion. And so there is this larger Indo-Australian entity that we think of as a composite plate. Maybe somebody can come up with a better, catchier name. So we also, as I want to point out again, diffuse oceanic plate boundaries between North and South America. A lot of textbooks still have a little line there, but if you go out to the place of the world, there is no line. It's a broad deforming zone, and we're still debating exactly where the pole of rotation is, but some of our analyses indicate it's also roughly in the middle of the boundary. Another one here, the Nubia-Somalia boundary comes out, we think it comes out, extends to the Southwest Indian Ridge over here, and we think the pole of rotation is right here. We switch from extension to contraction south of that. So very interesting phenomena. I can't go into more detail today. We've explored some of the physics of it. There's still a lot left to be done. Triple junctions. When we did Nouvelle, and then later when we did Morville, we found a number of the triple junctions didn't close. That was a statistically significant misfit. And 25 years ago, we were worried, well, we'll get new data and this will go away. But it hasn't gone away. It's still there. Usually the misfit's 1 or 2 millimeters a year, like around Bouvet. We have this big misfit at Galapagos, 14 or 15 millimeters a year. My student, Tua Zhang, has been working on this, and he's going to give a talk Friday morning at 8 a.m. and a geodesy session for anybody up that early. And we also published it recently in GRL. So we've knocked this down from 14 or 15 down to about 12, but it's still very significant. Okay, so thus, the plates aren't rigid. What could cause the non-rigidity? Dan and Don Turcotte proposed plate movement over non-spherical Earth. That's real. It's of the same order of magnitude, we think, as the thermal contraction effect. We've had a real tough time quantifying this well. We're still working on this. Horizontal thermal contraction of oceanic lithosphere, because we've been able to quantify this a bit more. Colette thought of it originally. We've explored it in a series of papers recently. I just want to show you the results from just one of these. Oh, not yet, sorry. Let's talk about the non-closure at the Galapagos triple junction. That's where the Pacific plate, the Cocos plate, all of which you can see here, and the Nazca plate, which you can see most of here, meet. The triple junction is right here, not an actual point because there's a microplate there. But then we can evaluate the velocities between these plates, estimate their angular velocities, evaluate the linear velocity at the triple junction. Let's start at the Cocos to the Pacific right here. We get a velocity that takes us over to here, and then we evaluate Pacific to Nazca, it gets us over to here. Then we take Nazca back to the Cocos, we get here, and it doesn't come back to the starting point. It's much bigger than the uncertainty. That's about 15 millimeters a year. Okay, now let's talk about thermal contraction. This is some work I did with Corné Kramer, where we tried to look at what the effect would be on displacement rates across the mega Pacific plate from the same thermal contraction models that Dan and John Sclater talked about. What we're showing in the top is strain rate, contours of the log of the second variant of the strain rate tensor. Black is contractional on the little strain orientation indicators. White is extensional. On the left, we inverted in a way to optimize to match the expected area changes. And on the right-hand side, we optimized to match the preserving shape so that circles would stay circles, for example. based on some other recent research, we think A is probably the better choice. So this is a realization of what that strain would look like. When we integrate it to get displacement rates, it really doesn't matter which one of these that we use because integration acts as a smoothing function. Here we show it for I forget which one of these. Here we've minimized the motion of geodetic sites that are on the old part of the Pacific plate. When we do that, then the most rapid motion is when you get far away from it. It comes out to about 10 millimeters a year relative to the old core of the plate. Alternatively, if we put it in a frame of reference right next to the Pacific Antarctic rise so we can see its impact on plate motion circuits, then we get the maximum motion up north. Once again, it's about 2 millimeters a year that would affect for a plate motion circuit. So if we're doing a global plate motion circuit, if we're getting 2 millimeters a year across every plate that has oceanic lithosphere, and all of them in the circuit do, and it's a random walk, then globally you should get a misfit of maybe 5 millimeters a year roughly. And so that's kind of your ultimate limit on how far you can push that rigid plate hypothesis. Okay, now I want to start talking a little bit more about space geodesy in my remaining minutes. The first thing we can do is this is the plate geometry we used in Morville, the paper where Chuck DeMetz is first author, 2010. It allows us to incorporate some plates we couldn't. Examples are Amur, Yangtze, and the Sundalam plate. Because we have geodesy, we can tie it into a continent which is adjacent to mid-ocean ridge and make a global model that way. Here we look at the example of Pacific North America motion. This is, I think, the first paper, as far as I know, where an angular velocity was published based on space geodesy. Don Argus was the first author. We use sites on the Pacific and from North America to estimate Pacific North America motion. Here's the polar rotation from marine geophysics, Nouvelle A in blue, and in red is what we found from space geodesy. Very long baseline interferometry indicates that, in fact, motion over decades is almost identical to what we see over millions of years. Okay, we can also use this to estimate the motion of the Sierras, which I mentioned in my introduction. It moves about 13 millimeters a year relative to North America. If we look at it relative to the Pacific, it's about 40 millimeters a year. And then using an oblique Mercator projection like Dan used in his first plate tectonics paper where he's looking at Pacific North America, here we're looking at Sierra microplate relative to the Pacific. And so if faults were parallel to plate motion, they should be horizontal lines here. You could see the San Andreas system cuts across it. And that means you have to be accommodating convergence here as well. For profile C, D, E, F, we see a substantial convergence, meaning several millimeters a year, and this is where we have coast range mountains. G, and H, the mountains are very low or non-existent, and in fact, this is where the watershed drains out to San Pablo Bay, San Francisco Bay, out to the Pacific. We see very little convergence right there. So this is a whole new tool we couldn't do from just marine geophysical data to understand something like this. Here we try to define a reference frame for North America, using just geodetic data. We minimize the reference frame in which all the sites in black minimize their velocity, so that would be stable North America. Blue is part of the diffuse plate boundary. They are moving relative to stable North America, and we exclude all the red sites because of the response to glacial rebound. We see rates of 1 to 3 millimeters a year, some of those statistically significant. And so that's, real deformation, what we see, but not on a long-term tectonic scale. I'm getting very close to the end here, 2 slides. So we look also speed differences between space geodesy as represented by Geodville and marine geophysics as represented by Morville. This is across mid-ocean ridges. The differences are small, less than 2 millimeters a year faster, up to 3 millimeters a year slower. So slightly more slower than faster, but on average, not that different from 0, maybe a slight slowdown. We can also look at subduction zones. Pacific Eurasia is faster. Nazca, South America, as is well known, is slower. The others are about the same. If we look at continental collision zones, Arabia, Eurasia looks like it's slowed down 7, 8 millimeters a year, as has India, Eurasia. And so we see a little bit of a net slowdown there. Possibly Nubia Eurasia has also slowed down a tiny amount. So since I've read this already, I'll just leave this for you to read, and thank you very much.
Any questions for Richard? Yes.
I have a simpler, catchier term for the transition zones, rigid plates and flying saucers.
Flying saucers, okay. I'll think about that. Thank you.
Okay, that's where plate tectonics is today. Now we'll hear about where it is not. Peter Molnar was a grad student at Lamont in the early days of the Revolution when the cause of deep earthquakes was still puzzling, and his early work with Brian Isaac showed they occurred in slabs of lithosphere that were sinking and exerting a downward pull that was an important part of the driving mechanism of plate tectonics. He also did some of the best work in marine tectonics with Tanya Atwater and others at Scripps and MIT, and anyone who's read all of his papers will wonder why it took anyone else so long to think of propagating rifts. I could go on for quite a while, but he asked me to keep this short. And of course, he's best known for his wide-ranging work on continental deformation and its effects, for which he won the 2014 Crawford Prize, the second of our speakers after Dan McKenzie to win this prize. Peter Molnar, who left MIT for the mountains and University of Colorado, today talking about from plate tectonics to continental dynamics.
Thanks, Dick. So if you're a seismologist, back in the days of plate tectonics, the iconic image that we have that really tells us what's going on is a map of global seismicity. This one from Mawia Barzanji and Jim Dorman. And you can see, of course, all the main features: mid-ocean ridges, transform faults, more mid-ocean ridges, subduction zones. They're all clear. This goes back 50 years ago. It was also clear right then, no question about it. The seismicity was diffuse in continents. It was spread out all over Asia, different parts of Asia, over the western part of the United States. So this was clear. We knew the continents were different right from the start. Today we can get at this maybe most easily with modern data using GPS, even better than earthquakes, hard as it is to believe. So this is a map showing GPS velocities. Everything's relative to Eurasia, so the yellow ones are showing points, GPS points, that are moving less than 2 millimeters a year relative to Eurasia, and then all the other ones, there's a scale 20 millimeters a year. India moves north-northeast, Arabia moves north-northeast, and then you have deformation spread over a large area. Those of us in the business think this is really continuous deformation. Let me just blow up one of these areas. There's a lot more data now, more than 10 years ago, but you can see India moving north towards Eurasia, again, all arrows relative to Eurasia, but divergence of flow on the eastern side, divergence out in here, shortening across a wide area. To us, it looks like continuous deformation. To put this in a perspective that maybe you haven't thought of, this is a painting by Camille Pissarro, one of the great masters of pointillism, Rue de l'Épicerie. This is the grocery street. And if you look at that, of course, you have no problem. The cathedral's back in here. The buildings are clear. But if you take a piece of it down in here where there's people and you blow them up, you can still see people in here. You wouldn't make any mistake about them being people. But then if you blew up another part, this is what you'd see. You wouldn't see people at all. This is kind of an image for where we are, where we've always been with continental tectonics. We can see a big picture, but sometimes the details are less clear. The details are important, but maybe less clear. The lesson that we learned from plate tectonics was stand back, look at the whole picture before deciding which details to study in order to understand some process or phenomenon. I don't in any way mean to suggest that this is not important. For Pissarro, it obviously was very important, and it's a really important part of the painting. But when you look at that, you're studying a different phenomenon from big, large buildings. One should always bear that in mind. So why is this difference between continents and oceans? Again, I think this has been obvious for a long time. If we plot strength in qualitative terms versus depth, in oceanic lithosphere over here, strength increases with depth because of friction. The greater the pressure at depth, the greater the frictional resistance, until you reach a depth where the rock is hot, plastic or viscous deformation can take place, and the region becomes weaker. When one moves into continents, one has different minerals. The dominant mineral in the mantle, of course, is olivine, but in continents you have quartz, feldspars, a bunch of other minerals. Quartz will flow at 350 degrees Celsius, whereas olivine, you have to get above 600, maybe as much as 800 for it to flow. So this quartz, at the same temperature as olivine, you can have viscous deformation within the crust. Feldspar is a little stronger, but the same process. Of course, the crust isn't just these simple minerals. There's a possibility you get increased strength with depth. But what you see in this, in a simple picture, is the core of the highest strength part of the mantle lithosphere in oceanic regions is removed, at least in some situations. And this weak, much weaker structure allows deformation to spread out over a large area. One doesn't make rigid plates. So you don't have rigid plates, but continuous deformation. The second most important part of continental deformation is you can thicken the crust. You can make mountains, like the Tibetan Plateau. This does not happen in plate tectonics. The crust is effectively constant in thickness once it's made. All you can do with it is subduct it and get it out of the way. Now I'm going to take you through some very elementary arguments, and I hope I don't insult too many of you with this, but I've discovered quite recently that a lot of people don't appreciate something quite simple. So suppose you have a mass, it's a height h above a surface, which is our reference. The potential energy is simply mass times gravity times the height, mgh. Now let this be a fluid-like object, or if maybe not fluid, but anyhow a continuous object that reaches to the same height h. It has density rho. The pressure at the bottom, therefore, is simply density times gravity times height, rho gh. The potential energy is, again, the mass times the mean height. Well, the mass is the density times the cross-sectional area times the height. That gets you the mass. Times gravity times the mean height, again, h over 2. So the potential energy is half rho gh squared delta A. And if you then look at what we really care about, the potential energy per unit area, it goes as the height squared. That's the main message that I'm going to pound away on for the next few slides. We can also look at this differently. Suppose it is a fluid, as you would have in a water tower, for instance. We'll let this fluid be infinite coming out of the page, so that it's just a 2D situation. You put a force per unit length along the walls to maintain the fluid, to keep it from collapsing. Well, that force per unit length is simply the average pressure times the height. The average pressure is a half rho gh, same pressure as we had before, times the height, and we get rho gh squared. An important message, the force per unit length is equal to the potential energy per unit area. Same thing here. And both are proportional to the square of the height. So you keep raising this, raising the level in here, you have to do an increasing amount of work, a non-linearly increasing amount of work. Double the height, the pressure at the bottom is twice as much, but the potential energy per unit area is the density, the mass is going up by 2, but the height is going up by 2, so you actually now, instead of having a half rho gh squared for the potential energy per unit area, you now have 2 rho gh squared. Double the height, quadruple the force per unit length. Mountain ranges and high plateaus should reach a limiting height. You can't lift them forever because the more and more work you have to do rises quickly with the height. And just one last one on this. Suppose instead you increase the area, the pressure is the same at the bottom, mass per unit, the potential energy per unit area is the same, regardless of how wide this is. Mountain ranges and high plateaus should reach a limiting height and grow wider. Now you're all thinking, yeah, come on, Molnar, but this is just water towers and things at a surface. What about isostasy? Okay, well, let's have isostasy. Let's take our crust, displace it to the right, thicken it so we get a mountain range that's little h high. We have a crustal root of delta h. That h should be up next to that. Because of isostasy, we have a simple relationship between the density difference between mantle and crust times the thickness of the excess root down here. That should equal the density of crust times that little height. And the potential energy has this. It has a term that goes with the square of that height, has a cross term, and then it has a term that goes with the square of this height down in here. Suppose we take the time derivative, differentiate this with respect to time. Obviously, Differentiating that, 2h squared, cancel out the 2. So we have a rho GH times a DH dt over here. Cross term is easy. I skip the algebra, but when you take advantage of isostasy, you wind up with this expression. The rate of change of the potential energy, simply the density of the crust times gravity times this quantity, which is the thickness of the crust. That's the crustal thickness. This piece up here plus that plus that. The rate of change is proportional to the rate of change of the height. But it's increasing as you thicken the crust. Eventually your crust is going to get so thick that you can't do this kind of work. And you wind up with a wide but not higher, not increasingly high area. So mountain ranges and high plateaus, you've got to do work against dissipative processes, of course. You have to do that in plate tectonics, friction or dissipation, but also against gravity. This really makes continents different, this aspect. The work done against gravity increases nonlinearly with the height. And so the high, wide Tibetan Plateau, which is spread out over a high, nearly uniform elevation, is the pressure gauge of Asia in this. Okay, Dan said something like this earlier, and I took this from one of his papers from 1977. The great success of plate tectonics came about because it separated the problem of the kinetic motions, plate motions, what Richard Gordon just talked about, from that of the driving mechanism. Driving mechanism is code for dynamics. This is not the case with continents. There's no such separation or simplification can be made for continental tectonics. It's like talking about kinematics of the atmosphere or the ocean. You can't do it. You have to know the dynamics. Continental regions deform as continuous media. Gravity resists the deformation, and these two are inextricably linked. This is why plate tectonics was accepted. We all thought it was wonderful. We moved on, and we still argue about continental tectonics. We all argue. So a couple of the questions that remain, just a small subset. Where does the strength lie? This is a cartoon. Obviously, this cartoon would look different if I gave you a different thermal profile. If I made it really cold, the entire crust would be brittle. The upper mantle would be brittle, as some of us think is actually the case. If you make it really hot, the mantle will have no strength, but you'd still have brittle strength up here. So in some sense, our problem is that different parts of the world are different from each other, but this is still a qualitative picture, despite wonderful work done by the rock mechanics, trying to constrain how to describe that. A second class of problems is what's the role of the mantle? The engine for continental tectonics lies in the mantle. So what's the role? In two parts of these, how and when is important here to me, have chemical differences between mantle lithosphere and asthenosphere manifested themselves? No question that Archean mantle lithosphere is chemically depleted. No one doubts that. Is this still happening? Okay, you can take your pick on that one. I have my opinion. How and to what extent is mantle lithosphere removed and replaced by asthenosphere as part of convective flow? Again, many of us have worked on this for years, and we still disagree. I'd like to leave you with the last slide, rigid plates versus continuous deformation, and seeing the big picture. This is Claude Monet, Île des Fleurs near Vétul. Thank you.
Questions for Peter? Yes.
How fast with GPS would I expect the mountains? I expect Tibet is going down at about a millimeter, I can't remember, about a millimeter every 10 years, I think, going down, because it's thinning. In the Himalaya, you have to be careful, because erosion is playing an important role. The peaks are going up, mean elevation isn't changing a bit, because the erosion has taken the rock away. That's my opinion.
Thanks, Peter. We're being kicked out. We're very fortunate that many of the scientists who made the key plate tectonic discoveries were so young at the time they can still be here 50 years later. I'd like to thank today's speakers for leading the way along paths. It's been so much fun to follow. And if anyone has any influence in Sweden, plate tectonics was one of the great scientific revolutions, and it would be great if 50 years later there were Nobel Prizes for some of the major contributors. Thank you for coming.